Today we're doing 8.5 logarithmic functions. Find the rule for the inverse of each function. So remember, we did this last half of the chapter. So this was the SSS. Whoops, sorry. Okay, there we go. Substitute, switch, and solve, if you don't recall. So it was S for substitute, which means we change the f of x to y. We switch x and y, so now we have x equals 2y plus 3, and we solve for y. So I subtract the 3, divide by the 2, so x minus 3 over 2 is y. Now we're taking that function and finding its inverse, and I take x minus 3 over 2. I substitute the y for the f of x. I switch the x and y. Solve for y. First, I'm going to multiply both sides by 2. That's going to get rid of the denominator. And then I have to add 3. So I end up with 2x plus 3 is my y value. Sure enough. There we go. What must be the value of x in each equation? Well, since we know that 8 is 2 to the 3, then x has to equal 3. And we know that 49 is 7 squared, so x has to equal 2. All right, to get this 9 into the numerator, we may give it a negative exponent. Oops. To the negative 1. Now we express 9 as a base of 3, so we get 3 to the negative 2, which means that x has to equal negative 2. Logarithmic functions, that's what we're learning about, are inverses of exponential functions. In other words, they undo it. So try to figure out what a logarithm is. If I tell you that log base 2 of 4 is equal to 2. Log base 3 of 9 is equal to 2. Log base 4 of 16 is also equal to 2. Well, notice that 2 squared is, jumping ahead, my hand hit it. 2 squared is equal to 4. 3 squared is equal to 9. 4 squared is equal to 16. So 5 squared is equal to 25. What exponent do I need on a 3 for it to equal 27? That's what a logarithm is finding, is the exponent needed. In this case, 3 to the 3, so the exponent needed is 3. What exponent on 2 is needed to get 8? Well, 8 is 2 cubed, so I need a 3. There we go. What exponent on 2 do I need to get 16? I need a 4. 2 to the 4 is 16. So that's what your logarithms are. They're basically exponents. The answer to a logarithm is the exponent needed for the base to become what's inside the logarithm. Equal to, apologize. All right. The logarithm of a number is the exponent when the number is expressed as a power of some number, like b. Okay, so log base 2 of 8 is 3 because 8 is 2 to the 3. Log base 3 of 1/9 was negative 2 because 1 over 9 was equal to 3 to the negative 2. Whoa. All right. Logarithmic functions, assuming b and x are positive numbers and b does not equal 1, y is equal to log base b of x if and only if x is equal to b to the y. That's how these logarithms work. You can rewrite using the definition the base to the outie, this is the outie, is equal to the innie. That's how that works. B to the y is equal to x. You can write it from an exponential form. Log base, well, in this case, b is my base of the x is equal to y, because the answer to a logarithm is always the exponent. Okay, convert to exponential form. Well, base to the outie, which you see right here, is equal to the innie. There we are. Base to the outie, 3 to the 1, is equal to what's inside my logarithm, 3. Base 10 to the negative 2 gives me 0.001. Remember this, I keep hitting with my hand. This is 1/100th. So it's 1 over 10 to the 2, which is 1 over 100. All right, example 2. Now we're going the other direction. We're taking an exponent and converting it to a log. So the base in this case is a 2. So that's why we have log base 2 over here. Okay, we have, actually I'm going to do this with a highlighter. That'll be nice. We have the base is 10. The exponent is 1. And the answer is 0. All right, again, base is 2. The exponent is negative 3. And the answer, what's inside my logarithm is the 1/8. Okay, I apologize. Now, evaluate log base 3 of 1 over 81. Well, first thing we do is we write the expression as an equation. Okay, that means I give it an equals y. Next, we rewrite the equation using the definition of the logarithm. In other words, the base to the outie is equal to the innie. Okay, so now I need to go back to my original methodology here of rewriting 81 as a base of 3. So I have to make this be 3 to the something. Well, that is 3 to the 4. But it's in the denominator, so I have to bring it up, making that 4 negative. So now I have 3 to the y is equal to negative 4, which tells me that negative 4 has to equal y. Okay. All right. Log base 2 of 8. Well, if I rewrite this as I'm using my definition. Okay, first, write it as an equation, so I have an equal y. Next, all right, next, you rewrite it, so I take the base to the outie, and that's equal to my innie. Okay, remember that 8 is equal to 2 to the 3. So therefore, y would equal 3. Okay, on this next one, on B here, log base 5 of 25. So the first thing we're going to do is, whoa, not that. I meant to, there we go. Sorry. Write it as an equation, so that's where the equals y comes from. And now I rewrite it using my definition, my base to the outie is equal the innie. Now I solve as previously learned, and that means I set 25 equal to 5 squared. So now the y is equal to 2. Solution. All right, move along. All right, log base 2 of 1 to the 4th. First step, write it as an equation. So I write that, whoops, I did it again. I keep thinking I'm changing to highlighting, and I'm not. Write it as an equation. That gives me the equals y. Next, I write it as I use the definition to rewrite. So I have 2, the base, to the outie, which is my y, equals the innie, which is the 1/4. Now I rewrite the 1/4 so that it's a 2 to the something or other. So this is 1 over 2 squared. I have to bring it up into the numerator, and that makes it -2. So now -2 is y. Okay, moving on to log base 9 of 3. First step, rewrite it as an equation. And I did it again, didn't I? Ah, well, there we go. Write it as an equation, and I'm going to get the equal y. Next step, write it as, use the definition, base to the outie equals the innie. Okay, now I can't make the 3 have a base of 9. That just doesn't work. But I can have the 9 be a base of 3. So that's what we're going to do. So 9 is equal to 3 squared. I'm just going to do that. There we go. So I have 3 squared, that's a 2, to the y equals 3. Well, we know that that means 3 to the 2y is equal to 3. So we know that the 3 has a 1 exponent, so 2y has to equal 1, so y has to equal 1/2. All right. Inverse property of exponential and logarithmic functions. What this says is these things can cancel each other out if we plug them into each other. So notice if I take b to the x and I plug it into a log base b, I'm going to get x. In essence, these two will cancel each other out, and I'm just left with x. Okay, this is because, now the other thing we can do is rewrite this using the formula, right? Using the definition. So if I rewrite this, I have, whoops, I'm going to do this in highlighter. I have base b to the outie is equal to the innie. B to the x equals b to the x. We know this to be true, always. All right, now let's look at the next one. The same idea here. It's inverse, so it's going to cancel. Because if I write this as defined, base b, I'm sorry, this is the exponential. Sorry. Okay. All right. The base is b, so I write it as, ew, that's yellow. That's not showing up. The base b, the base is b, the exponent is the outie, right? So this would be the outie right here. Well, there it is, the outie. And it's equal to the innie. Well, here's equal to the any, and here's my any. Oh, that's right. This is written incorrectly. This should just be equals x, not b to the x. Okay. We're getting there. Base 10 logarithms are frequently used because we use a decimal system. These are called common logarithms. And basically what that's telling you is that log x, notice that it does not have a base on it. No base. When it's just log x, that means by definition log base 10. Okay, because log base 10 is our common, what we work with every day. Now, if you look on your calculator, most scientific calculators will have a log, just log x. Okay, so you can find log base 10 of anything because it's x. Because it's base 10. Sorry, it's on your calculator. All right. That's what your common log is, just log. All right, an exponential function. We already learned this. The exponential function, y equals b to the x. Remember the graph was exponential growth or exponential decay. It was one of the two, growth or decay. Notice it's getting to all x values. So your domain is all real because it's getting to all x values. On the other hand, your range is wherever the asymptote was, in this case 0 or greater. Okay, but it can't ever equal to 0 because it's an asymptote and it never quite gets there. Now, for an exponential function, my graph is the other direction. Like that, because it's the inverse, it's actually rotated across this x equal y line. Okay. So, exponential. Now we have an asymptote of, nope, not y, sorry, x is equal to 0. Here we had a y equals 0 asymptote. Now we have x equals 0 asymptote. So my asymptote is actually that. In this case, the y-axis. But that means that my range is now all real, but my domain is the one being restricted. So my range is all real numbers because it gets to everything both directions. But my domain now is restricted to being greater than 0. So domain and range have flipped. This is another indicator that these are inverse functions. All right, 15. The graph of y equals log base b of x. Okay, y equal b to the x, you can see is the red line. The blue is log base b of x. So, the x-intercept, the x-intercept is is 1 comma 0. The vertical asymptote is x equals 0. All right, you always will have b comma 1. Okay, notice b is the base. So this one they've sketched is 2 because I have 2 comma 1. And 1 over b, negative 1. So this would be basically 1/2 over here. So these are the common points you'll have. And we'll talk about exactly picking points. Everything. All right, equations of the form. Now this is the same equation, except for notice we now have h and we have k as well as a. So we have a, h, and k again. Remember, a changes the shape. It stretches it or compresses it. H is your horizontal shift. All right, let me do this. Okay, so A stretches the graph or compresses the graph. H shifts it horizontally. And K shifts it vertically. Okay. Wow. All right, now graph y equals 3 log base 2 of x plus 4. Well, this is how they do it, but I find that to be a little confusing when you throw in, it's fine if I don't have a, but if you throw in an a, it's not as easy. So what I prefer to do is I draw myself a points table, an XY table. Oops, let me get it a little darker. So I have X, Y, but what I really need to know is this portion in here, I need to have it be very specific things. So I'm going to, first off, let's rewrite this. Okay, that's how I find my points, is I rewrite this. I'm going to use my definition to rewrite it. So I have the base is 2. The space to the outie is equal the innie. The thing is, I have that weird 3. So what this is really saying, if I divide this by 3, this is y over 3. Sorry. Oops, it erased it somehow. Okay, y over 3. So it's y over 3 is my exponent. Okay, what I need is for the y over 3 to be whole numbers. Because I'm not real great at finding the square root of 2, or the third root of 2, or the whatever. Okay, you get the idea here. So what I want is, I'm going to be picking my y values. So I need y over 3 to equal specific numbers. So I'm going to choose, if y over 3 to be 0, that means y has to be 0. If y over 3 is 1, then y has to be 3. If it's -1, then y has to be -3. So I can do it with these 3 points. So now I'm plugging into my equation. I have 2 to the y over 3 minus 4 is equal to x. That's what I've got to find is x. So 2 to the y over 3. Well, y over 3 is 0. Well, 2 to the 0 then is 1. Minus 4 is -3. Okay, so what I did is I did 2 to the 0 over 3 minus 4 equals, well, this portion is 1. Okay, so since that's 1, minus 4 is -3. That's my x value. So now I'm going to do 2 to the 3, see, here's my y, over 3. That's 1. So 2 to the 1 minus 4, that's 2 minus 4 is -2. So I have a -2 here. All right, and if you notice, I have a 0, -3. So a -3, 0, -3 in the x, 0 in the y. Yep, there it is. I have a -2 in the x and 3 in the y. Yep, there it is. And for -1, I plug that in. I get a 2 to the -1, which is 1/2. Minus 4 is 3.5. And sure enough, I have a -3.5. There it is. Not 3/2, pardon. Sorry, that was 3.5, which is 3 times 2 is 6, so 7/2. So this is a negative 7/2. Or you could write it as 3.5, I just don't have space. And that's this point. And that's sufficient points to graph this. Okay, I know it's confusing, but that's what I would do. It's a little bit easier, I think, than all of this translating and stuff. Okay, so now we're done. And thank you for listening.